A scientist records the height of a plant over several weeks. So you have weeks here, and then you have the height here. Use the line, find a line of best fit in the form of y equals mx plus b. Use this equation to estimate the plant's height at week 10. And is this model linear growth? Justify your answer based on the data. So what we're going to do now is look at this data right over here. We're going to enter that in our TI-84 calculator. So what we're going to do is we're going to press stat, and then we are going to press edit. And then you have L1, L2. L1 is reserved for the x values. So the x values are 1, 2, 3, 4, 5, 6, 7. Let's do that. 1, 2, 3, 4, 5, 6, 7. And then the y values, these values right over here, just match them up with the corresponding x values. So it's going to be 4. Then you're going to have 7, 9, let me see, 11, 13, 16, 18. All right. Now what we're going to do is we're going to go back to stat. We're going to go to calc, and we're going to go to linreg. Okay. We're going to go to linreg, and I'm just going to press calculate it. And then this is our line of best fit. So this is y equals ax plus b. So in this case, it's going to be y is equal to a. We know a is 2.29. So y is equal to 2.29 plus 2. Let's write that down. Y is equal to 2.29x and then plus 2. All right. Use the equation to estimate the plant's height at week 10. So this is basically, this line of best fit is basically a sort of estimate for what's going on right over here, right? And so what we're going to do now is we just plug in 10 into x, right? So yeah, because look at our data right over here, right? We only have, for our x values, we only have 1 week, 2 week, 3 weeks, all the way up to 7 weeks. However, we're trying to find out the plant's height at week 10, right? So what we do is we can construct a line of best fit to sort of kind of estimate, the plant's height, assuming that this sort of trend goes on until week 10, right? So we're using the line of best fit to sort of kind of estimate, what's going to happen if we, generated sort of more and more data. So at week 10, I plug in 10 in for x. So it's going to be, 2.29 times 10, and then it's going to be plus 2. So it's going to be 24.9 centimeters. If you plug this into your calculator, you get that. All right, is this model linear growth? Justify your answer based on the data. So, the first thing that I notice is that as the amount of weeks increase, the plant growth, the height of the plant increases. Okay, so this is something known as a sort of positive correlation. Basically, as one thing goes up, the other thing goes up as well. However, what you have to know is that there's a difference between a correlation and a causation. All right. So think about it like this. So let's say that if I give out this statement, did you know that 100% of people who drink water die? All right, that's a true statement, right? But does that mean that water causes people to die? No, right? So there's a difference between causation and a correlation. Correlation, okay, you might see a little trend in what's happening, but causation, something being correlated to another thing doesn't mean that it causes the other thing, right? For an example of like a causation relationship would be if I study more, then my test grade increases, right? That's like the sort of simplest example, right? And in this case, is this considered a correlation, or is this considered sort of only a correlation, or is there some causation to this trend right over here? So, feel free to pause the video and sort of answer this. Well, this data right over here shows that as the amount of weeks increase, or the height of the plant increases. So does that mean that time affects plant height? So some people might say that, the amount of time affects plant height, right? As time goes on, the plant height increases. However, you have to know that there's also, other factors, other sort of variables that come into play when you're examining sort of plant height, right? How much sunlight is this plant getting, right? How much water am I giving this plant? So just saying that only time affects the plant height isn't really an accurate statement. It's more of like time, adequate amount of sunlight, and adequate amount of water affects plant height. That would be like a more accurate statement. Then you could say that that causes the plant height to increase. But just saying that time affects plant height, that's not really a causation. Because what if you don't feed the plant any water, right? Then the plant height's going to decrease and the plant's going to die. So it's like, yeah. Is this model linear growth? Justify your answer based on the data. So to see if something is linear growth, or a linear model is a good suit for that, what we're going to do is you're going to press second catalog, and you're just going to go all the way down to diagnostic on. You're going to press enter, and it's going to turn it on. Now you're going to go to stat, calc, and then linreg ax plus b, and it's going to give you this r value. So just pay attention to this r value. In this case, our r value is equal to 0.0998. Now, R values is basically the correlation coefficient, and R value is always in between -1 and 1. If something has an R value of 1, that means that there's a very strong positive correlation. So in this case, right, we have a positive correlation because as one thing increases, the other thing increases, right? That's a positive correlation. However, if something has a correlation that's very close to -1, so for example, if I have an R value of, let's say, -0.9, that symbolizes that, the two variables you're discussing have a negative strong correlation, meaning that as one thing increases, as one variable increases, the other variable decreases, right? And it's a strong correlation, right? So that's basically all that is saying. All right. And in this case, since our R value is very close to +1, that basically just means that, this model right over here, or, this line of best fit that I've drawn, this y is equal to 2.29x plus 2, that's a very good representation of what's going on here. All right, there's a strong, positive correlation between our, weeks and then this height in centimeters for the y value. That's all that is saying. And, you can also plot a residual plot. So you can also do something known as a residual plot. Because think about it, right? The line of best fit gives you an estimate for what this data represents. But sometimes this line of best fit might not be, the best at accurately representing the data. So then, to determine if, you want to use a sort of quadratic sort of line of best fit or use an exponential or a logarithmic line of best fit, you're going to, to find out, you're just going to plot this residual plot right over here. So how does this work? Well, for starters, right, we're just going to focus on these y values right over here and, the corresponding x values. You got to look at this data. And what you got to do is for each respective x value, find out what that is when you plug it into the line of best fit. So let me show you what I mean. So our line of best fit is y is equal to 2.29x plus 2. All right. Now what we're going to do is we're going to press second table, and we're just going to list out all of these y values from x is equal to 1 to x is equal to 7, because that's what's going on for the x values right over here, right? We're seeing, how the plant height changes as we go from week 1 to week 7. So, using our line of best fit, we can also estimate this using that, that equation. So when x is equal to 1, the y value is 4.29. When x is equal to 2, our y value is 6.58. When x value is 3, it's 8.87. X value is 5, 13. When x value is 4, 11.16. X value is 5, we have 13.45. X value is 6, we have 15.74. And then when our x value is 7, we have 18.08. So let me just make a new column. So this is our x values, this is the y values from our data, and then this is the y values that we got when we put our, the corresponding x value into the line of best fit. Obviously, the line of best fit isn't perfect, which explains, little bits of discrepancies. But notice how, the line of best fit actually, represents our data pretty well, right? Because our line of best fit values right over here, they are very close to the actual values, which means it's a pretty good accurate representation of the data. And what we can do is we can plot a residual plot. So what we're going to do is we're going to subtract the height of this by the corresponding sort of height value that you get from the line of best fit. So when I subtract 4 from 4.29, I get negative 0.29. When I subtract 7 from 6.58, I'm going to get 0.42. When I subtract 9 from 8, I get 0.13. When I get subtract 11 from this, I get negative 0.16. Subtract this from this, I get negative 13.45. This is 0.045. Subtract this from this, I get 0.26. And when I subtract this from this, I get negative 0.03. Right, so, and then we have all of this data right over here. Now this data basically just represents this data right over here, actual minus expected. So right, all we're doing, all this data represents is the actual values, in this case, the actual height minus the expected height. So basically the expected height represents, when we plugged in x is equal to 1 into, our line of best fit, right? Our expected values are just the line of best fit values. And then when we subtract these two values together, we get the kind of discrepancy between the actual value and the expected value. Now, what we can do is we can graph all of this data right over here onto something known as a residual plot. So let me just label. So we're going to use our x values. So remember, our x values are 1, 2, 3, 4, 5, 6, 7. And then what we're going to do for our y values, we're going to plot this actual minus expected, right? We're going to plot, this residual, basically. So, when x is equal to 1, this discrepancy is negative 0.29. When x is equal to 2, then we have 0.42. When x is equal to 3, we have 0.13. X is equal to 4, we have negative 0.16. X is equal to 5, we have negative 0.45. X is equal to 6, we have 0.26. And then, when x is equal to 7, we have negative 0.03. All right, and this is our residual plot. It basically plots the discrepancies between the two values. And notice how there's no pattern, right? There seems to be like no pattern in this residual plot. And the important thing to know is that if there's no pattern, then the line of best fit is a good representation of the data. So notice how in our residual plot, there seems to be no trend, which means that this line of best fit that we have right over here is a pretty good accurate representation of the data. And, we also kind of see that from, just the discrepancies itself, right? It's very small, but since there's no trend, this is kind of like another reason why this line of best fit is very good for the data. If I had a residual plot that maybe looks something like this, where this is basically my x value, this is basically my y values, and it looks something like this, where maybe there was like a little pattern, like something like that, then our residual plot, then our line of best fit would not accurately represent our data, and we might have to use another type of line of best fit. All right, now this is an example of when a residual plot isn't, actually shows that a line of best fit isn't a good representation of the data. Now, obviously for this data right over here, you can see that this is an exponential sort of trend, right? As our x increases, y increases dramatically. However, this right over here is obviously a linear line of best fit because it's y is equal to mx plus b, right? So we're using a linear model to represent an exponential model. So, I'm a little suspicious about that, but let's see. Let's see if, it is a good, who knows? You never know. So what I'm going to do now is I'm going to basically have a scatter plot. And the scatter plot is basically just a plot with all the data, right? So when x is equal to 1, y is equal to 0, when x is equal to 1, y is equal to 0, x is equal to 2, y is equal to 10, and, so on, right? And then this seems to be the trend. So let's see, here, 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 and then all the way up here. 1, 2, 3, 4, 5, 6. All right, we have 6 points. And let's just say I graph my line of best fit. So let's say my line of best fit looks something like this. Let's say my line of best fit looks something like this. I know this isn't the best drawing. I'm sorry. All right. Now, this isn't the line of best fit for this model. I just kind of made something up. But let's just say that it looks like this for the sake of me being lazy. Now, remember that if I want to plot a residual thing, what I have to do is I have to take my actual value and I have to subtract it from the expected value, right? So it's going to be the actual value minus the expected value. And in the context of a scatter plot, this is what it looks like. So we know that our actual values are represented by these little dots that I've made, right? And our expected value is represented by this line, right? Because that's the line of best fit, right? So the actual minus expected value would just be the difference of these two values, right? The residual, this would be the difference between these two values, right? It would be the difference between these two values. Be the difference between these two. It would be the difference in between these two, right? It would be the difference in between these two. So this is kind of how you visualize, how I get the residual plot from an actual scatter plot. Now, take a look at here. So, when x is equal to 1, our residual is around 0, let's just say. When x is equal to 2, maybe it's like a little bit below. X is equal to 3, maybe it's like a little less below. But then notice here, right? Then it starts to increase. So now it starts to increase, right? Right over here. This is a pretty big difference in the actual minus expected, right? It's a pretty big difference in actual minus expected. And in the final one, this is a very, very big difference. It's a very, very big difference in the sort of actual minus expected value, right? And notice how it creates an exponential trend, right? I know this you might interpret it as sort of like a quadratic trend, but because I didn't draw that well, it looks like a quadratic trend. But let's just say this is an exponential trend because that's what the data is saying. Sorry if my drawing's bad, but yeah, notice how our residual plot represents what's going on here, right? What's going on in my actual graph or my actual data is that this is an exponential growth. So what happens is my residual plot is going to show exponential growth if I use in this case this linear sort of thing, right? Because linear sort of the line of best fit for kind of a linear graph doesn't really work well for an exponential sort of data, right? So it's not going to match up. And just by looking at the line of best fit, well, you can tell if it's a good match or if it's not. If it's random, it's like a random residual plot, it's good. But if it's not random and it shows a trend like this one, well, it's time to switch to a new line of best fit.